Welcome dear students once again into the class of number theory, and we are starting with from where we have left in the last lectures, in the lecture of the chapter of binary quadratic forms. So let us start with the reduced forms. So I am defining reduced binary quadratic form. So what is a reduced binary quadratic form? A binary quadratic form fxy is equal to ax square plus bxy plus cy square is said to be in its reduced form, or is said to be reduced binary quadratic form if either minus a is less than b is less than or equal to a is less than c. Either this condition is satisfied, or 0 is less than or equal to b is less than or equal to a is equal to c, or this condition is satisfied. If either of these two conditions is satisfied, we say that the binary quadratic form ax square plus bxy plus cy square is a reduced form. So this is the basic definition, and for every discriminant d, there are exactly a finite number of reduced forms, and suppose for a particular binary quadratic form there are n reduced form for the particular discriminant d, then n is called the class number of the discriminant minus d. That we'll see later on, but first start with the definition of reduced binary quadratic form. Now, next is the definition of proper and improper representation of a number by a binary quadratic form. So, write down the definition: proper and improper representation. Proper and improper representation. Suppose fxy is equal to ax square plus bxy plus cy square be any binary quadratic form, and let n be any integer. Let n be any integer. If there exist integers x0 and y0 such that fx0 y0 is equal to n, then we say that n is represented by the binary quadratic form. If there are integers x0 and y0 satisfying this condition, that means f of x0 y0 gives you the result equal to the integer n, then we say that n is represented by the binary quadratic form ax square plus bxy plus cy square. Moreover, if GCD of these two integers x0 and y0 is 1, that means they are co-prime, then we say that this representation is a proper representation. One thing is to be clear, that number of representation may not be unique. There may be 2, there may be 3, there may be 10, 20, 30 representation of n by a particular binary quadratic form. And there may be proper, or these representation may be improper. But the one for which the GCD of x0 and y0 is 1 will be called the proper representation of n by the binary quadratic form ax square plus bxy plus cy square. Now, we will move on to a theorem, a very simple result, a very trivial result you can say, that the number of representations of n by any binary quadratic form fxy is equal to ax square plus bxy plus cy square is either 0 or finite. There, it is not necessary that every natural number is represented by a particular binary quadratic form. Some natural numbers may not be represented by the particular binary quadratic form, and if it is represented at all, then the number of representations must be finite. So this is the theorem. Write down theorem number of representations of an integer n by a binary quadratic form fxy is 0 or finite. It may be 0, it may be finite. It cannot be infinite, in fact. So how to prove this result? Prove, let the given binary quadratic form be fxy is equal to ax square plus bxy plus cy square. Let it not be taken as given. So take binary, you can say take binary quadratic form, because if we say that let the given binary quadratic form, that means we are talking about some particular. Here we are not talking about some particular binary quadratic form. We have taken just a general binary quadratic form, and we will show that the number of possibilities of the coefficients a, b and c, these are finite, and once these choices are finite, the number of binary quadratic forms will become finite, or it may be 0. We have seen in a previous video that this fxy, which is in this form, can also be written as 1 upon 4a, then 2ax plus by whole square minus discriminant dy square. It can also be written in this form. Now what we want n to be represented by this binary quadratic form. That means we want fxy to be equal to n. So suppose your fxy is equal to n. Suppose your fxy is equal to n. Now take this 4a by cross multiplication to the other side. You will get 2ax plus by whole square minus dy square is equal to 4an. Move one step further, take this term to the right hand side. That means minus dy square is equal to 4an minus 2ax plus by whole square. Now 4an minus something positive because it is a perfect square. 4an minus something positive will definitely be less than or equal to 4an. So this quantity is going to be less than or equal to 4an. Or you can say that your 4an is 4an minus this is going to be, this is not dy square, this is minus dy square. This is minus dy square. So minus dy square is less than or equal to 4an. Now what is d? Since we are considering this d to be negative, minus d will become positive, and take it to the other side. Your y square will be less than or equal to 4an upon minus d. So that means your y is less than or equal to under root 4an upon minus d. Now that means the number of choices of y are finite now. Number of choices of y are finite. And if you substitute the value of y here, these finite number of values, suppose there are 10 values. So these 10 values, you substitute these here. Corresponding to each y, you will have at the most 2x, because it will become a quadratic equation in x. And it will give you at the most 2 values. So corresponding to these m values of y, there are at the most 2m values of x. And these m values of y and 2m values of x they'll give you a finite number of pairs of x and y. So how many representations will be there? Will be definitely finitely many, or maybe zero if there is no y satisfying this condition. So the number of representation of an integer n by a binary quadratic form is either 0 or is finite. So we have proved this theorem, and this result we will prove it, we will use this result in proving some questions and understanding the concept clearly. And even this 4an, you can take this 4 outside, you can write it 2 under the root an upon minus d. So this result I am going to write somewhere here on the board because I may need it for some questions. So it is y is less than or equal to 2 under the root an upon minus d. This result I may use for the illustrative questions to make the concept more and more clear. Before going on to the next questions, results, theorems or lemmas, let me rub the board first. Now, this binary quadratic form fxy is equal to ax square plus bxy plus cy square. If you substitute the values of x and y, some different pairs of x and y, what you are going to get? You are going to get different numbers as a result. These may be positive, these may be negative, maybe 0, but definitely there will be a least positive integer represented by this form. So the question arises, what the least positive number is represented by this binary quadratic form. Suppose I am going to write some binary quadratic form. I am writing 5x square plus 14xy plus 11y square. My question is, what is the smallest, the least positive integer that is being represented by this binary quadratic form? You may say 1, but it is not true. Sometimes a binary quadratic form, it may not represent 1. It may not represent 2, it may not represent 3. Maybe may it be representing the least positive integer. It may be 4, it may be 5, it may be 10. So we don't know which least positive integer is being represented by a particular binary quadratic form. So how to find it? So there is a procedure, there is a method, there are some steps to be followed to find the least positive integer represented by this binary quadratic form. So what you have to do, step 1, take n to be minimum of a minus 1 and c minus 1. A and c are here given. For every binary quadratic form, a, b, c will be given. So take n to be the minimum of a minus 1 and c minus 1. Step 2, apply this result. That is, you can take mod y, because earlier you were having here y square. So by taking the positive square root both sides, you may apply here the mod. So second step, apply mod y less than or equal to 2 under the root an upon minus d. What you will get from here, you will get some values of y. You will get some values of y. You may get some 2 values, 3 values, 4 values, 10 values, but the number of values will definitely be finite. So you will get some finite number of values of y from this inequality. Now step 3. Step 3. Find corresponding values of x such that your 2ax plus by square is less than or equal to 4an plus dy square. This result we have earlier used. So this result we will apply, we will substitute the values of y, and we are going to get some possible values of x, and we will make the pairs of xy then. So what is the next step? Find fxy for these possible pairs of, or you can say possible finite number of pairs of xy, and observe the least positive integer represented by fxy. This is the procedure. Now, how to use this procedure? So, I have written one binary quadratic form here. So, I am going to use this one to illustrate this procedure, this method. So, here this is your fxy. What is your a here? Your a is 5, your b is 14, your c is 11. So, I am moving now step by step. In the first step, what I am to do? I am to find the value of n such that n is the minimum of a minus 1 and c minus 1. So a minus 1, your a is 5, so 5 minus 1 is 4, and c is 11, so c minus 1 is 10. So n is minimum of 4 and 10. So what is the minimum of 4 and 10? Is clearly it is 4. So minimum of 4 and 10 is 4. So we have obtained the value of n. Now substitute the value of a, n and d here in this equation. So you are having mod y less than or equal to 2 under the root a n by d. I am writing it a little back so that I will get some space to write it. Mod y is less than or equal to under the root 2 times a n upon minus d. What is your a? A is 5 into n. N we have just obtained 4 over minus d. So minus, and d is the discriminant, b square minus 4ac. So b square 196 minus 4ac. 4 into 5 20, 20 into 11 220. So this is your 2 under the root a n upon minus d, or you can say it is 2 under the root, here you will get 196 minus 220. This is minus 24 and there is a minus outside, so you will get 24. So you will get 24 here, 24, this is cancelled, this is 5 by 6. So 2 under the root 5 by 6. And 5 by 6 is less than 1. So definitely under root of 5 by 6 is also less than 1. So this quantity is going to be less than 2. This quantity is going to be less than 2. That means your mod y is less than 2. I am writing it again. So what you are going to get from here, that mod y is less than 2, strictly less than 2. And if your mod y is strictly less than 2, what possible values of y are there? The possible values of y are minus 1, 0 and 1. There is no other integer that satisfies this condition. So these are the only possible values of y because of this condition. Now we have to find the corresponding values of x from here. So one by one I will put y to be minus 1 here, I will find x, I will put y to be 0 here, I will find x, I will put y to be 1 here and I will find x. So let me start with y is equal to minus 1. If I put y to be equal to minus 1 in this equation, you will get 2ax plus by. B is 14 and y is minus 1. I am taking this one, the first case. So it is minus 14 square is less than or equal to 4an. 4a is 5, 20, 20 into n. N was 4, 20 into 4 is 80 plus dy square. Your d is minus 196, it was minus 24. Minus 24 into y square is 1. So it is 2ax minus 14 square is going to be less than or equal to 56. What is A? A is your 5, so it is 10x minus 14 square is less than or equal to 56. Now use your hit and trial method. You put x to be 0 here, then the inequality will not be satisfied. You put your x to be 1, 10 minus 14 minus 4 square is less than or equal to 56 is okay. So one of the values you are going to obtain is x is equal to 1, because x is equal to 1 satisfies this equation. You take x to be 2, 10 into 2 is 20, 20 minus 14, 6, 6 square, 36 is less than or equal to 56 is again okay. So value of x is 2 also possible in this case. If you take x to be 3, then 30 minus 14 is 16, 16 square is 256, less than or equal to 56 is absurd, is not possible. So these are the two values corresponding to the value y is equal to minus 1. So I have obtained two pairs. What these two pairs are? 1 minus 1, 1 minus 1, and then 2 minus 1. 2 minus 1. Two pairs I have obtained. Now I'll move on to the next value of y, that is 0. Now substitute 0 in your equation. In this equation, you put y to be equal to 0. So a is fixed, 10, sorry 5, 2 into 5 is 10, so it is 10x plus by. Y this time is 0, so it is 0, or you can write plus 0 square is less than or equal to 4an 80, we have already seen, and the right hand side is already fixed. I think it is 56. Earlier we have also obtained that it is 56. It will be fixed now. Now in this equation, once again use hit and trial method. If you take x to be equal to 0, 0 less than or equal to 56 is okay, very good. So one of the values obtained is x is equal to 0. If you put x to be equal to minus 1 or 1, you will get 100 here. 100 less than or equal to 56 is not possible. So there is only one value of x in this case. And the pair obtained is x is 0, y is 0. So this is the pair x is 0 and y is 0. Now the third case, your y is 1. We have completed the first two cases. Now I am moving on to the third case, y is equal to 1. When y is equal to 1, this term plus by will become plus 14 here. Plus 14 here. Now once again go on to hit and trial. For 0 not possible, 1, 2 the quantity will be increasing, not possible. Take x to be minus 1 or minus 2. If you take minus 1, it is 16 less than or equal to 56, okay. If you take x to be minus 2, it is 36 less than or equal to 56, once again okay. So the two values are minus 1 and minus 2, and the two pairs are minus 1, 1, minus 1, 1, and the other pair is minus 2, 1. So these are the all possible pairs we have obtained. And now move on to the final step. The final step says that now find out the values, all the values for these pairs of the binary quadratic form. That means f of 1 minus 1, f of 2 minus 1, f of 0, 0, f of minus 1, 1, and f of minus 2, 1. Find out these values. 1 minus 1, you substitute it here. So 5, 1 square plus 14 into 1 into minus 1 plus 11 into minus 1 square. So what you are going to get? 5 minus 14 minus 9 plus 11. So it is 2. Now 2 and minus 1. So 5, 2 square plus 14, 2 minus 1 plus 11 minus 1 square. So what is the result? What is the value? It is 20 minus 28. So minus 8 plus 11 is 3. Now f0, 0. Clearly it will be 0. As x is 0, y is also 0. But we have to leave it because we have to find the least positive integer represented by the form, and 0 is neither positive nor negative, so we will have to leave it. From the rest of the numbers we will find which is the least positive integer represented by this binary quadratic form. Now minus 1 and 1. 5, we have 2, we have 3. If the rest of the two numbers will be greater than or equal to 3 or greater than or equal to 2, the least number represented by this binary quadratic form will be 2. And if any one of these will give you the result as 1, the least positive integer represented will be 1. So let us see what the next two results are. 5 minus 1 square plus 14 minus 1 into 1 plus 11 1 square. So let us see what the value is. It is 5 minus 14 minus 9 plus 11 is once again it is 2, and 5 into minus 2 square plus 14 into minus 2 into minus 1 plus 11 into 1 square. So it is 20 minus 28 is minus 8, minus 8 plus 11 is once again it is 3. So out of these four now, what is the least positive integer represented by this binary quadratic form is clearly 2. So 2 is the least positive integer represented by this binary quadratic form. fxy is equal to 5x square plus 14xy plus 11y square. Answer is not 1 because 1 is not being represented by this binary quadratic form. So this is the procedure, this is the way, this is the method how to find the least positive integer represented by a particular binary quadratic form. So with this theorem, with this illustration, with this example, I am going to close this video lecture here. In the next lecture we'll learn more and more about binary quadratic forms. Till then, thank you once again.